Back again, we are in the PLC Professor's workshop studio. This is going to be part 3 of the discussion of the largest lab project in our lab project manuals, and that is the virtual machine. And we're going to go through a lot of features. We have something I call a poor man's HMI, and that's where we create rungs of logic with bits that toggle on and off with different steps, different part locations in the machine in a way that's easy to watch your product going through the process. We also go a little bit further with being able to get more than one part into that workstation at a time. You will also see some logic for sequencing that's not in the newer set of manuals. This is the newer set. The two red and black ones, 2020 edition. Okay, these don't have any sequencer instructions. And the reason we pulled them out is because most universities and colleges didn't want to eat up their class time dealing with the sequencer instructions, because most folks, at least people who write programs, don't use them anymore. The problem is that if you're going to work out in the field in a manufacturing facility, you're going to have really old equipment, and it's going to have sequencer instructions. Sequencer in, sequencer out, and sequencer load. Sequencers used to be a major component of industrial manufacturing, the automation, the control part. So there are older manuals that you might have. For instance, this set right here, Beginner and Beginner Plus. These do have the sequencers in them. This Collegiate Edition, which is the predecessor of those other two red and black ones, it may not. So we might include some bonus lectures that discuss sequencers in more detail, but that doesn't mean you have lab projects that those videos support. But rather than not include them in the lecture access for you, we've decided we're going to throw in some things and call them bonus lectures. That's not what we're doing right now. Right now we're just going to go complete the virtual machine with the way it is in the current 2020 set of the manuals. So let's do that. More discussion of our virtual machine. Now we're going to do an output routine. Typically, most programmers create a separate subroutine with all of the output logic in it, meaning rungs that the result is turning on and off an output bit, and then they put all the logic specifically for that output, just turning it on and off in either manual or auto mode into that rung. And then from the other routine, the main routine or the sequence routine, comes the actual result, the logic that actually tells that bit to either go on or off. But it makes it easier to troubleshoot because you go to one routine, you can find the output that you're looking for, and then work your way backwards with either search or with cross-reference to find the logic that's actually controlling that part of the sequence. As you can see here, looking over at our main program, we now have 5 routines. The main routine, the barcode reader. We'll open up the barcode reader. You see that's not changed. When we get a barcode trigger, we're pushing a value greater than 5,000 into part number, which we clear. So that is not changed. The main routine is going to change. Cylinders will not change. We've got outputs and sensors. And we move some logic around. Keep in mind that we've got something called sensors. Well, I'll just double click and open that. Remember that we had these pseudo sensors that we added, and you see that we now have these aliased to virtual I/O. So local 3 iData bit 10, but see that underscore? That's a virtual I/O. That's not a real I/O module. We just did this to make it look like it was I/O, which if this were a real process, we would have some real inputs. This would be the input here, and because this no part at cylinder 3 extend is part of that virtual I/O process, we moved it into this routine. So we just took some of this virtual I/O stuff and moved it into the sensors routine. What's of interest to us is the outputs. So we've taken our actual outputs that were in the main routine. We'll open that up. And so we no longer have, you can see that I kind of collapsed the project view or the Explorer here to give us more width for our logic. Before we had a kind of an output that we called barcode, read barcode. So that would be an output bit, so to speak, that goes to the barcode reader. So if I look at this read barcode and I do a cross-reference, I see that it's used in outputs. Double click on that and you can see here that that read barcode, if you're in the auto mode, will set this bit high for whatever length of time that this logic is true, which you can see is for 3 seconds. So if we have a new part blocking the photo eye, then for 3 seconds we're going to get a trigger pulse. Now it doesn't have to be 3 seconds. 1 second is more than enough. Matter of fact, I don't even know why it's 3 seconds. It only needs to be 1 second, half a second. It would probably work okay if it was 1/10 of a second. The reason that we create a pulse is part of the interface between the PLC and other electronics, in this case the trigger input on the barcode scanner. Back to the outputs routine. So here's our, this is a real output here, cylinder 1, cylinder 2 extend. So if you look, we have safety logic here, if you want to call it machine safety. In other words, if cylinder 3 is extended, then this would be false. So this is the retracted prox. So cylinder 3 has to be retracted, otherwise we cannot extend cylinder 1 and cylinder 2 for obvious reasons, right? And we don't want cylinder 1 and 2 to extend no matter that we're in the auto mode or in the manual mode. Now this input right here, or this bit, HMI, extend cylinder 1 and 2 push button. That would be a bit controlled by your panel view, your HMI, your MMI, operator terminal. That in the manual mode, you could extend and retract cylinder 1, cylinder 2. But these two conditions right here override the auto and the manual mode, so we cannot extend cylinder 1, 2 unless cylinder 3 is retracted and we are not telling cylinder 3 to extend. Let's say that somehow, somewhere else in the program, we turned on the solenoid to extend cylinder 3. And if this were extended, it would crash into it. So the instant that you tell this to extend, this is going to go off and 1 and 2 are going to retract. Now there still may be a collision if cylinder 3 got extended faster than you could retract cylinder 1 and 2. And the reason we do it this way, we have both of these in here, is because this won't change state as fast as this. So if you turn off this bit, then you're going to retract cylinder 3, right? After a very short delay, this will no longer be true. But this will go false faster than this. Typically, I like to put my outputs in numerical order. So you see I have local 10, data 0, data 1, data 2, data 3, and so forth. That's to make it easier to find for the maintenance people or anyone who's trying to analyze this program. So you're out on the shop floor, something's not working, and they're saying, well, the drill, it's turning on, but it's not, the cylinder's not pushing it into the part. Well, you would go looking for this bit right here to see why it wasn't on. And if it is on and the cylinder's not extending, then you've got another problem. But the starting point is always the outputs, because typically when you walk up to a machine and you say, all right, what's going on? The operator tells you what it's not doing. In other words, you walk up and say, what's wrong with it? They say, well, it's not finishing the part. Well, what's it not doing? Well, it's not drilling a hole in the part. So you look at it and you see that the solenoid, well, you see the cylinder didn't extend. Well, you can do several things here before you go get your laptop and plug in. First of all, you can look at the LED on the controller I/O module to see if this bit is turned on. In other words, there's an LED that will light up. Now, if this was a 1400 or 1000 or RSLogix, some of them have LEDs, some of them have a LCD display, and you can put it into I/O display and you can look to see if it's getting turned on. Now, just because the controller says it turned it on doesn't mean you've got voltage actually going out there to the solenoid. So the next step would be to go out to the valve bank, the valve manifold, and if you've got the good solenoid valves, they have a little LED or light on them to show you if they're energized. If that LED is off, then you can assume that if the LED on the controller is on, but the LED on the solenoid valve is off, then you got a problem in between. So then you go get your meter, you throw your meter on that output terminal, and you see there's voltage there. Okay, so the voltage is leaving the controller. Now you've got to go out to the valve and see why it's not turning on the solenoid. Now, the voltage may be reaching the right point, but the solenoid could be burned out or the LED's burned out, but that's not part of this course. But you see why being able to quickly find the outputs is very important. So you look here and you see we have the same pattern throughout. We have an auto mode and a manual mode. In the manual mode, all that you have really is an HMI button to tell it to, you push the button, it extends, you release, it retracts. This is so you can manually operate. Now, let's say you were doing troubleshooting. Okay, and you clear out the machine, you got a problem with cylinder 4, you put it in the manual mode, and then you start operating the push button. Now, if this works, then it's not the hardware. In other words, if you can manually get this to energize and it extends a cylinder, then the problem has to be right here. Whatever you're using in the auto mode, which would be this logic right here. So if we click on that and cross-reference and look for the OTE in the main routine, here's the logic that says to extend cylinder 4. We used to have an output here, an output bit. Now you can use cross-reference to get back there, but you don't have to. Go to the output, and that bit has now been replaced with an internal bit put as part of this entire logic to control that actual output. So all that we did in the main routine, we took and replaced all of the OTE instructions that actually set bits that control outputs. We replaced it with an internal bit or a bit of station 1. Now these, you could call these steps, except that we're not latching them. But as long as we have to have a non-IO bit, which I created a station 1 as probably a double integer. We'll go look. See if we put it in controller tags. No, put it in program tags. Okay, if we go down to station 1, there it is right there. So you see it's a dent. And that gives us station 1.0 through 32. And of course, we don't need that many bits. So as long as we had to have a internal bit, so to speak, or a non-IO bit, I figured why not name in station 1 and then put, bit 0, 1, 2, 3, 4, 5, and so on. That way, if you need to know what's going on in the logic, you can look at these bits sequentially to see the sequence. So looking at our outputs, we have all of our outputs here. Now we have some that are virtual. Okay, this is not a real output here. Anytime you see the local underscore, that's virtual. That's real. So cylinder 5, cylinder 4, 3, 1 and 2, those are real outputs. These others are virtual outputs that we created to look like outputs. So we take all of our output devices, we put it in the output file, and for logic we have auto mode, manual mode, and then we fill in what we want for auto mode and manual mode. And of course we add these safeties. We don't want to turn on the finished product conveyor if cylinder 3 is not retracted. So that logically moved from the main program, so to speak, into the output file. We added these 3 rungs with no operation outputs, meaning that these rungs don't actually execute. They simply are here so we can see the state of these bits. So you see we have station 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have some real inputs, photo I1, photo I2, photo I3, and then these are pseudo or virtual. See the underscore, local underscore 3. And then we have some outputs, output 0, 1, 2, 3. And then we have some virtual outputs, barcode trigger, drill motor, and finished product conveyor. This is all here just for you to observe while you're executing the logic. So to run this, we would push the reset button to clear. In this case, all that we're clearing are any of these virtual outputs. Executing this logic, first thing we would see is photo I1 sees a part. So I'm going to turn that on, and we're starting to pulse to read the barcode. Okay, and we got a good part number. The part number is over 5,000. We have a timer, and it just timed out, 10 seconds. So if photo I2 doesn't see that part within 10 seconds, someone could walk by and throw their hand in front of the photo I and mess with stuff. So we have a 10-second timeout. So let's do that again. We turn on photo I1, and it scans in a 5,555. And then we turn on photo I2, and it extends cylinder 1 and cylinder 2. We're in the auto mode, so see, we're sequencing right through. If I go down here and watch, finished product conveyor is running, cylinder 5 is extended. We have a part at cylinder 3 end of stroke. So I've extended this, and this is still running because we haven't declared that it reached stop number 2. So if I turn on photo I3, now you see the finished product conveyor stops, and we show a part that's setting in front of the stop at cylinder 5. So we have one part in the system. If we put another part in the system, we would turn on photo I1 and photo I2 and extend cylinder 1, cylinder 2, energize the drill motor, and you'll see that extends cylinder 4, retract cylinder 4. Once it's retracted, we extend cylinder 3, and then we retract cylinder 3, but we don't go any further, simply because we can't run the finished product conveyor because we have a part sitting in front of photo I3. So right now we have a part sitting in front of photo I3, and we have one at the end of stroke for cylinder 3. So now we can run in another part. Turn on photo I1, turn on photo I2, And this part should end up at end of stroke for cylinder 1 and 2. So see, now we have photo I4 and photo I5, part at cylinder 2 end of stroke, part at cylinder 3 end of stroke, and a part at photo I3. That's as far as we can go. And at this point we would have to have a downstream call, which we don't. And I could turn on that downstream call, but we'll just leave it at this. In the next section of the manual, we kind of, in order to give significant coverage to the idea of sequencing and the different methods, we showed another method which is not very popular, but it's very easy to understand, and it more resembles the original sequencer instructions, which we will also talk about a little bit. We're not going to spend a lot of time on either one of these simply because you probably will not write programs using either one of these styles, but you're going to be in a position probably where you will have to troubleshoot and analyze logic written in these forms by your predecessors. So, we kind of skipped ahead a little bit here. In the manual we had if the position is equal to 0 and if station 1 sequence word 0 is equal to local 1I data, and then we upgrade it to a mask because we wanted to ignore certain bits and only compare specific bits. Now the reason you would do that is, let's say you only had 3 or 4 bits that you wanted to look at on that input card. So that's a 16-bit input card, local 1I data. Typically it's going to be a 16-bit card. Well, let's say there's only 3 or 4 inputs there that you want to look at. You're going to use a mask, and then you're going to come up with values based on the bit patterns. This is our stepper here, if you like. If you're in position 0 and the input card, local 1I data, matches your stored value for station 1 sequence or word 0, you're going to turn on the match found bit. And the match found bit down here one shots and add to add 1 to the position. And then of course here we have if you're equal to 4, then you clear and you go back to the beginning because we have only a few steps here. So every time, whatever step you're in, 0, 1, 2, or 3, you can't get from 0 to 1 without completing 0, and you can't get from 1 to 2 without completing 1. So there isn't any other way this can work. If you're in step 0 and the inputs are equal, you have a match found and the next run down adds 1. Now you're in step 1. When it's equal to this, match found, now you're in step 2, and so forth. However, remember that the change in local 1I data, those are sensors or switches. Something has to happen in the process, and we do that over in the sequencer output routine. I'll geezer that down just a little bit so you can see there's only 4 rungs. We'll go back up here. So when you're in position 1, remember you start in 0, and to try to put this in a better perspective, you start in 0 and nothing really happens in 0, but the sequence isn't going to move forward until these bits right here match. So we're looking for a value of 1 in local 1I data. Now the process isn't going to cause that, the operator will. So when they have the switches in the right position, or they jogged everything back to the home position, then this bit pattern for local 1I data will match this word, match found. Now you're in step 1. When you go to step 1, in this logic, it's waiting for the input module to go from a value of 1 to a value of 2. But that's only going to happen because in this rung, when position went to 1, this was true, and it took this bit pattern, station 1 sequence outputs, and moved it into that output word, which is going to turn on an actuator, motor, something. And that's going to cause a change in the sensors back here in this word. And when it reaches a value of 2, that would be the first bit turns off and the second bit turns on. So that first bit here that had to be on to get you out of step 0 into step 1, when it goes off and the next one comes on, match found, now you're going to step to position 2 or step 2. When you do that, see, position equal to 2, it moves a different bit pattern into the output, and so forth. It just goes right on through. It's that simple, really. So that's about all there is to say about this formula. And of course we threw in the masking simply because in our little projects we control everything. So we really didn't have to mask to compare the source and the compare value of local 1I data. We did not need to use a mask because we don't have logic turning on any of the bits. But in the real world, you're more than likely, if you find this type of sequencing, you're going to find they use mask equals. And remember that these inputs that they're looking at for their pattern, it could be input 2, input 7, input 14, and input 15. It could be those 4 bits, and you mask everything else because you only want to compare this change in those specific inputs. Here we have the next form of logic, and that's using the sequencer input and sequencer output instructions. Both of these instructions require a control data type that has a position and a length. And we are buffering our I/O simply to avoid, because remember this is the Logix engine. And the I/O update is not synchronous with the program scan. Inputs can change state and show up different in the memory anywhere during the program scan. So to prevent that, we buffered our I/O. We have it all baked into one rung here. So we buffer our inputs into a double integer, and then that double integer dent buffer word 0 you see is using sequencer input, and then we're going to put the results into another double integer buffer word 1, and then that gets moved into the output bits. Now the sequencer input and sequencer output instructions work identical to the logic that we just looked at. So the sequencer input is looking at that value right there, double integer buffer 0, and it's comparing it to the first word of these 4 words. And when they're equal, then the control data type will step 1, which will cause this to step 1, and put a different word from the source here into our output word that's going to go out to the outputs. This sequencer input steps every time the source is equal to the array, and when this is true, then this is going to take and move a different value from the array into the destination. So these 2 instructions right here are the logic. These are just there to buffer the I/O. And you don't see much of this sequencer in and sequencer output instructions used anymore. They're more difficult to troubleshoot. We have a solid example of those in the manual. We also had this convoluted subroutine control here, and we took the first 3 bits of a word enable logic, and we used those to control which logic we used out of our sequencer, whether we used CLN sequencer or the sequencer input, sequencer output, or we used the SQI, SQO instructions. Another little variation that we did, which is the same thing as buffering the I/O, we did mapped inputs and mapped outputs. So you see we are still using internal words here. So our source is we're looking at station 1 inputs image, which is the result of this logic, and then we're moving the results to station 1 outputs image, which in this routine, we could go to that routine, mapped outputs, and you see that we're using those bits to actually control the outputs. And that pretty much wraps it up for the manual. I realized that we did a little skimpy discussion on that last section, and we've actually removed that section from some of the newer manuals because it just wasn't very popular. However, I wanted to include just enough discussion so if you run into the sequencer input, sequencer output instructions, and there's also a SQL, sequencer load instruction. If you run into these instructions, you have at least heard a little discussion on them. I would strongly advise against using them when you're writing code. They're very difficult to troubleshoot, and if you want to add a step, it is very problematic, because remember that you're working with an array of words, and if each word in the array is a bit pattern for a step, and you've got 17 steps in your sequence, and you want to add a step between step 4 and step 5, you got to move 5 through 17 down one word to put in the new word. So it's very cumbersome. Strongly recommend against using the sequencer instructions.